Hey everyone, in this video, we're going to see how to compute 50 million primes in 5 seconds. If you haven't seen my previous video on the sieve of Eratosthenes, make sure you watch that one first. I'm going to start off with the code from that video and then try to make it fast. So I thought that I would come back to this code that we wrote on the sieve of Eratosthenes for finding prime numbers and just see, what are its limits. I'm thinking that 50 million primes or so should be a good amount. Let's just go ahead and see if this code is fast enough. Okay, so I went ahead and just killed that. As you can see from the memory usage, that wasn't going to finish. So if you're not clear on why this blew up my memory, here's the line that did it. So the first step in the algorithm is to make an array that will fit all of these 10 to the 9 numbers. And it didn't throw an out of memory error, but it certainly ran through all of my RAM and was going to start using disk, and that's not going to be fast enough. So I don't think that I can necessarily efficiently work with an array of size 1 billion, but there are only 50 million primes less than that. So why am I making an array of size 1 billion when there are only 50 million primes? So I think the next step is to do this in a kind of segmented fashion. Basically, I'll use something similar to this algorithm, but I'll do it in chunks. So I'll look at a big chunk of numbers, not 10 to the 9 big, but maybe 1 million or something like that. And then I'll do something like this for those million numbers. And then since most of the numbers are not going to be prime, I'm not going to have this huge array that's stored in memory. I'm just going to be storing the prime numbers, and I only need to make this segment, which stores all the numbers, big enough to fit, however many I want to check at a time. Okay, so here's what I came up with. Basically, I'm going to add primes in segments of squares. So let me tell you what I kind of mean by that. Basically, these are all of the primes that are less than or equal to the square of 3. And this end segment is going to be telling me which prime I'm using. So index 1 tells me 3. So this means I've got all of the primes less than or equal to the square of 3. Well, if I know all the primes up to the square of 3, then to find all the primes up to the square of 5, I just need to check these primes as the multiples. So that's what this extend method does. It goes through and it says, okay, you've found all the primes up to the square of this number, and then it's going to go in and find all of the primes up to the square of the next one. So this is just some bookkeeping of numbers here. I'm keeping track of this segment, which is the square of p to the square of q, where p here is like 3 and q is 5. It's the next one. I'm making a big array, which is representing all the numbers in this range. And the important part here is that although this is a big array, it's nowhere near as big as all the numbers up to q squared. It's just the numbers between p squared and q squared. So that's what's going to keep our memory usage way down compared to the last algorithm. But once we decide on what the segment is, the algorithm is basically the same as the plain old sieve of Eratosthenes. I go through each of my prime numbers, find the ones which are in the range, p squared to q squared, and then using this slice syntax, I just mark them as false. So this is a little bit of a confusing looking line. Basically, all this does is assign the value false to all of the indices from the minimum of the segment up to the maximum of the segment in multiples of the prime. And I just do that for each prime. Then I go through and I look which things are still marked prime. I add those primes to my list of primes, and then I go through and mark it as saying that, now I've moved the 3 up to 5, meaning I found all the prime numbers up to the square of 5. So here's how I use the sieve in order to count the number of primes less than a certain target value. I start by making a sieve, and then remember the sieve stores, the primes that it's found so far. So I just look at what's the last prime that I've found so far, and then check to see if it's bigger than my target. And if the biggest prime that I found so far is still less than my target, then I just keep adding more and more primes until the biggest one is bigger than my target. At that point, I can go in and check how many primes are less than the target value. Now, this seems a little bit inefficient, and it is, but you have to remember that because I add primes in big chunks, I may have skipped way over my target value when I do an extend. So I do have to go in and check which ones are less than the target. It's not like I'm adding them one at a time. Then I'm just timing it and printing it out. So let's go ahead and run it. Okay, so it looks like it did finally finish. And okay, so it gave me the right number, but you see that this took 233 seconds. That's too slow. So I could just save the prime numbers to a big file, and then this runtime wouldn't be as much of an issue. But I was really looking more for a solution where I could just, whenever I needed to, load up however many prime numbers I needed without having to read or write from a file, something like that. So I think I'm going to go a different route and try something else, try to make this even faster. So try number 2, this time I've switched out all of the Python lists for NumPy arrays. The advantage of doing this is that NumPy arrays do a lot of operations in C that might otherwise happen in Python if you were using Python lists. Now, C code is much, much faster generally than Python code, and so I'm hoping to squeeze just a little bit more performance out of using these NumPy arrays. So here are the changes. I've added a data type. Of course, now we might need to worry about overflow, but I don't think we're going to overflow anything just with the first 50 million primes. Most of the bookkeeping stuff is still the same. Everything pretty much had a one-for-one replacement from pure Python to NumPy. That's pretty convenient. I like that NumPy has this kind of slice assignment where I can just say assign everything to false. That's much easier than what I had to do in the Python side. So I do know that NumPy arrays have this resize method, which I think will come in handy. It basically allows you to resize the array in place, so you don't have to copy the initial segment of the array. You just have to put in the new elements. Whereas a concatenate, this is going to make a totally new array, so it's going to copy all the existing primes and all the new primes. But sometimes resize can fail, so that's why I have this try catch here. Other than that, it's pretty much the exact same. I've moved out this count primes less or equal into its own function. Just keep extending until I have found a prime that's bigger than the target number. And then before I was converting everything to a Python list and then checking. That's not going to work because just iterating over all these primes on the Python side is going to take way too long. I'm just going to try to keep everything in NumPy arrays. So I'm actually going to do a bisect right, which is going to tell me where I would insert this number n into my array. So it's basically going to tell me how many things are less than it. So that kind of gives me a log time way to find the number of things that are less than a given number in the array. All right, let's go ahead and see if it works. Okay, finished this time in 104 seconds. Twice as fast, but not great. I'm going to go ahead and profile this and see what the problem is. Okay, after profiling, I see that most of the time is spent in this resize or concatenate function, which tells me that these segments might be too small. Maybe I should do more at a time. So currently, if I know all the primes up to the square of 3, then when I extend, I find all the primes up to the square of 5. So I just look at the next prime. I think that in order to speed this up even further, the best thing to do is to just make it jump more than one at a time. So let's just set like a target value of jumping 100 primes at a time, and then just see if that can get rid of some of the time spent copying. All right, so I went ahead and I added in this extend at most n segments target. So this is just going to tell us, how many primes ahead do we want to look at a time. Before we were just doing 1. So now I'm going to say try and do 100. Of course, initially I don't have 100 primes to work with, but it will pretty quickly get up to the point where I can go 100 primes at a time. So I just changed this to extend at most n segments at a time. Now it takes this parameter n. This used to just be 1, and then this is like the maximum number of primes that I could extend by. And then I just replace that n in these places. And other than that, everything else is the same. as you can see, I went ahead and ran it, and this time it's only 12.25 seconds. So a huge speed increase just by increasing the segment length effectively by adding this parameter that allows us to do multiple segments at the same time. This allowed us to essentially avoid recopying data over and over again. So 12.25 seconds for 50 million primes. That's plenty fast enough for me. That's a lot faster than I was expecting to get in Python. So I think that is where I'm going to leave it. Just kidding. I rewrote it in the simplest possible way in C++, and now it's down to 5 seconds. Thanks for watching. Hey everyone, hope you liked the video. I spent so much time on the Python side of this code that I decided to actually go ahead and make this into a pip installable library. So if you want to use this code, I added a whole bunch of helper functions, kind of things that would help you look around with prime numbers. You know, what are the primes in a certain range? What's the nth prime number? What's the index of a certain prime number? Counting how many primes less than a number, counting how many primes in a range, stuff like that. It's now up online on PyPI, and to install it, all you have to do is pip install prime-civ, and that will download and install all this code.